Okay, people, last example, example 5. Now we're going to actually take this to the real world, compare two log functions. All right, I'm going to read from over here. Logarithmic functions can approximate the altitude of a plane over time, which is so true. Think about it. Last time you were on a plane, I know it might be a while ago, maybe for some of us, never, but you can absolutely envision this. What happens on a plane? You skyrocket, right? You build up speed on the runway, you start increasing your altitude super quickly. All of a sudden, you're gaining a lot of height in a really short amount of time. And then you kind of start to level off a little bit. And that's exactly what a logarithmic function looks like. You increase, right? You increase rapidly, and then you kind of start to level off. So that's exactly what a log looks like. So what we're going to do is we're going to compare two logs and find out which plane's altitude shows the greater average rate of change over the interval 10 to 15. So there's two different planes, plane A, plane B. We're given some information, and we're just going to go find the average rate of change, which is really like our same formula for essentially finding the slope. Okay, so let's talk about plane A. What are we given? We're given a function that says its altitude is 9,200 times the natural log of t plus 10,000. Okay, so of course, in order to find their rate of change, we need to know what the actual altitude is at 10 minutes and then 15. So we need to find A of 10 and we need to find A of 15. Okay, so A of 10, we're going to plug 10 in for t. So 9,200 times natural log of 10 plus 10,000. Doing that right in my calculator because our ln button is right next to the 4. So 9,200 ln 10, close the parenthesis, plus 10,000. We get 31,183.78. And if we plug in and evaluate at 15, we're going to get 9,200 times the natural log of 15 plus 10,000, same thing, 9,200 ln 15, close your parenthesis, plus 10,000, 34,914.06. Okay, so now, right, we have our two altitudes. So to find the average rate of change, we're going to do our change in y over our change in x, or our change in altitude over the amount of time. So 34,119 minus 31,183 over the time interval from 15 minus 10. So 34,914.06 minus 31,183.78. We get 3,730.28 over 5. So on average, plane A is increasing its altitude at about 746. What are we talking in feet? All right, so the average rate of change is about 746 feet per minute. So let's see how that compares to plane B. So what's nice about plane B is that we're actually given our points. We have a point of 10, 37,497 and 15, 39,449. Okay, once again, we know that our average rate of change is the change in altitude over the change in time. So 39,449 minus 37,497 over 15 minus 10. 39,449 minus 37,497. So we get 1952 over 5. So the average rate of change for this plane is about 390 feet per minute. So, we're being asked, which plane's altitude shows a greater rate of change over that time interval? Certainly much greater. So plane A has a greater average rate of change. And that's strictly just from one of these. In plane A, we had to evaluate at a couple given t or x values in this case. Plane B, we were given some data. We know that average rate of change is the same idea as finding slope. And naturally, one of these planes is climbing significantly more over that same time period. So really, it just must mean that plane B had kind of already reached its cruising altitude, and really plane A still really needed to climb. So over that 10 to 15 minutes after takeoff, plane A was still climbing. Either way, we could do a little comparing, do a little rate of change. Bada bang, bada boom. Using logs. Well done.